Today I'm going to talk to you guys about total revenue. The unit that we're moving into is 1.2, and that's about elasticities. And elasticities is basically a further study of demand. One part of it's about supply. It's a further study of how demand is different for different products. A lot of what we're concerned with as we look at elasticity, especially the first type, price elasticity of demand, is concerned with the effect that a price change has on total revenue for the producer. So we're looking at if the producer could see the demand curve, what would be the optimal place for them to put the price to maximize the amount of revenue that they receive from sale of the good or of the service. When we look at total revenue, it's the formula is simply price times quantity. Now remember, most of our analysis in economics, we're going to set a price, and then based on the demand curve, we're going to get a quantity as a result. So the price we set times the quantity that results from the price that we chose to do. We bring in the thinking that is just a simple geometric concept, and on here, that's always going to create some sort of rectangle. So when we go from a price of 4 over to the demand curve, and then down, we end up with this kind of tall blue rectangle. So price times quantity is the same as our formula for the area of a rectangle, which is base times height. Now I suppose in economics we would say height times base, because we like to do price first. But either way. So let's go ahead and look at this new rectangle that I just drew, and it's got a base of 2 and a height of 4. So it's 2 times 4, and the total revenue of this, the total revenue when I set the price at 4 would then be 8. The original one I have in here, we see that the total revenue, again, is price times quantity. So it's a height of 3, price of 3, and then a base of 3. So 3 times 3, total revenue of 9. Well, if we look at those two results, so the first result was 4 times 2, so the blue had a total revenue of 8, whereas the one that I already had drawn in, the black square, it has total revenue of 9. So based on that, we can see that it would be better for the producer in terms of total revenue. Keep in mind, we don't know anything about cost yet. We're just talking about total revenue, so we can't say profit. But in terms of total revenue, obviously 9 is a better number than 8. So in our analysis, we could point out that 3 is going to be the best price for this producer to set. When we do that analysis, what we can do to make our analysis a bit more clean is we can take these 1, 2, 3 rectangles that are created by our overlapping boxes. By the way, we call this, when we do this, we call it a revenue box. So we can take the 1, 2, 3 rectangles and figure out, what's the area of each of those rectangles. So this biggest rectangle, this is 3 times 2, so this has an area of 6. That rectangle is pretty important because if you notice, whether I set the price at 4 or whether I set the price at 3, we are going to always get this rectangle of 6. That's not part of what I gain or lose by changing my price. The other 2 rectangles, though, they are. If I set the price at 4, that means that I get this small rectangle, but I don't get this tall rectangle over here. This one, it's got a height of 1 and then a base of 2, so it's worth 2. And remember, 6 plus 2, that's going to be our 8. This other rectangle that we get if I do set the price at 3, not 4, it's got a base of 1 and a height of 3. So it's worth 3. And that's 6 plus 3, that's our 9. So again, this makes it real easy to have an opportunity cost discussion because I can say the opportunity cost of me setting my price at 4 is I give up 3 to get 2. Well, obviously that's not a very good deal. If you don't set your price at the middle point of the demand curve, and by middle point I mean the maximum point was 0 to 6, so 3 here, so it's the midpoint there, it's also 0 to 6 there, so 3 is the midpoint there. And if you put this on pause and hold your ruler up to the screen, you would also find that along the length of the demand curve, this is also the middle point of that. If you don't set the price at that middle point, you're going to find that your total revenue won't be maximized. So I already showed you if the price was above that, our total revenue was less. Let's look at a price below. What if we set the price at 2? So again, we have this big box is worth 6. Now this one here is 1 times 3. And this one is 1 times 2. So if I move my price from 3 to 2, we go from there to there, and I lose 3 to get 2. Again, that's not going to be a situation that works out very well for me. The same is true no matter what happens to the shape or the angle of the demand curve. No matter what, that middle point is going to be the best place for us to put the price. It's going to maximize our total revenue. This is going to hold true no matter what happens to the angle of the demand curve. No matter what you do to the scale, no matter what you do to the prices that you're looking at, this is always going to hold true. Let's look at the second demand curve and figure this out. So here, we see that when price is 2, the midpoint is here. So when price is 2, quantity demanded is 3, so total revenue is going to be 6. Let's see what happens if we take the price that was the best total revenue here and get the total revenue for this one. Now looking at this curve, when I come over from 3, it's a bit hard for me to see what that number is. Now I think it's probably 1.5, but let's go confirm. Let's write the formula for this demand curve. It's quantity demanded equals A, which is 6, the x-intercept, minus, and we need to find the d variable, and remember that's going to be run over rise. So 6 over 4, and that's going to reduce down to 1.5. So this is our formula. We can plug in 2 real quickly here and confirm that. So if I do 6 minus 1.5 times 2, 1.5 times 2 is 3, so 6 minus 3 is 3. Now let's see what happens if the price is 3. So 6 minus 1.5 times 3 is going to be 1.5. So now we've got 2 times 1.5, so that's worth 3. And now we've got 1 times 1.5, so that's worth 1.5. So our total revenue there is going to be 3 plus 1.5, and that's going to be 4.5. So when price is 3, total revenue is 4.5. To finish this off, this would be 1.5, a run of 1.5 with high to 2, so that's going to be worth 3 as well. So if I go from price 2 to price 3, will I lose 3 to get 1.5? So the rule here, the rule that we're trying to get to, is that for every demand curve, total revenue is maximized at the middle point of that demand curve, no matter what the demand curve looks like. However, if you look in your book, or maybe some books, if you look at other videos on the internet, other economics teachers, even myself, a lot of times we will make it seem like there's an exception to this rule. So let's investigate some of those exceptions real quickly. Let's have a look at this demand curve here. And what we have is we have a rise of 12 and a run of 6. So our midpoint, our rise of 12, our midpoint is going to be right here where 6 is. Now first thing we should notice is that when we bring this down to 5, 5 is clearly not the midpoint on our run. So something's amiss here, something's a little bit different. But let's go ahead and investigate the theory for a second. So let's go from 6, and theoretically, based on our rule, that should be the maximum total revenue. So if we draw our boxes and then maybe go over here to 4 and draw our boxes, what you would find out is that you would be giving up 6 to get 20 when I increase the price. So I've moved away from the midpoint, and moving away from the midpoint should always reduce your total revenue. I've moved away from the midpoint, yet I gave up 6 to get 20. So my total revenue is going to go up. Again, specifically, this middle point would be 6 times 4, so 24. So if my price was 6, my total revenue would be 30, 24 plus 6. But if my price were 11, my total revenue would be 44. So what gives? Well, again, let's go back to the problem we saw right here. And essentially what is happening is we're not looking at the whole demand curve. Because I had this cut off, because we had the demand curve wasn't touching the y-axis, what that really meant was I'm only looking at a portion of the full demand curve. And if I cut it off here, I'm saying that, well, when the price is 12, we have demand of, I don't know, whatever it was, 3.5 or something like that. But what happens when I raise the price higher? For some reason, I'm not showing that. And we'll do this a lot in economics. There's reasons for it, but you just need to get used to it. So if we look at the full demand curve, so the demand curve does keep going until it hits the y-axis, but oftentimes we just sort of omit that part. If we look at the whole demand curve, obviously that was not the middle of that demand curve. The middle of that demand curve is going to be somewhere up here. So both of these prices are in the lower half of the demand curve. And remember I said a second ago, the closer and closer and closer you get to the middle, the higher your total revenue is going to be. So actually what I showed before confirms that. Our first total revenue was 30, and as we got the price closer to the middle, somewhere up here, our total revenue increased to 44. So actually, instead of disproving the rule, instead of being an exception, it actually confirms the rule. If you look at the whole demand curve, which you should know in your mind, it's out there, even if you're not seeing it. On the flip side, we'll often show a demand curve that looks like this. It's relatively flat, whereas this one was relatively steep. Well, again, you can see here, if I move from, so this is 6 times 4, so again, 24. So again, here we're showing a total revenue of 30, and that is the theoretical middle of that demand curve. And as I move away from it, theoretically, total revenue should decline, but it doesn't. It goes from 30 to 48. But just like what we saw in that example, you're not seeing the whole demand curve. And when you look at the whole demand curve, again, you see that because total revenue is increasing, it must mean you're getting closer and closer and closer to the middle point. So the middle point, if you look at the whole demand curve, clearly it's in here somewhere. So don't let these are very common things that you'll see out there. Don't get confused with those. Again, there's a reason for doing it, but make sure that you think about where's the whole demand curve. Okay, so some conclusions. All demand curves, and by the way, we only look at in IB, we only look at linear demand curves. In more advanced economics, they do look at, demand curves that are curved, and then that's not going to hold true. But all linear demand curves do follow the total revenue rule that we've created. The rule, again, total revenue is maximized at the middle point of the demand curve. When you make a comparison, when you compare two demand curves, it's only valid if the scale of the demand curves is shared. So we see that here. So these two demand curves, this one is more steep than that one, we can make some comparisons about those two demand curves. But again, for D2, remember, we're only seeing the upper half of that demand curve. The rest of it is out here somewhere, we're just not seeing it. So we can make valid comparisons here, and we can make valid comparisons if we're comparing two segments on one demand curve. So we can make a comparison about the blue shift or the blue slide down the demand curve versus the red one. What isn't valid is if you just kind of randomly take two demand curves and draw them and try to compare those two curves and say, look, this one is more steep than that one, so there's going to be some sort of difference between the two. Well, it's not valid because I can make the beginning and ending point of that demand curve 4 and 10, likewise with that, and now all of a sudden it's the exact same demand curve. It's just that I've taken this one and stretched it out a little bit, but I haven't actually changed any of its mathematical properties.